Okay, we can start though. So if you take the very first line and hit shift return, you should get the butterfly graph. You got that? So we're going to calculate the two sparsifiers of the butterfly graph. Okay. So the next command is the Laplacian. So you can try it yourself. Do you know how to get rid of the output? So it's a little, it's easier to demonstrate it. So if you go to the extreme right, there are these brackets, long brackets that sit next to every input and output. Do you see them?
We can show it here.
Oh, it's coming up? Okay. So, okay, let's try. Okay, so my version, I removed all the outputs, so let's have a look. So this is the butterfly graph, okay. So what I mean is, do you see if you go to this end, there are these long square brackets, yeah? So if I go to the square bracket that corresponds to the butterfly graph and I click on it, I get this, okay? And then if I do delete, the butterfly graph goes away, okay? Don't delete the inputs, but delete the you can delete the outputs. Anyway, you saw how to do that, right? Okay, then we're good. So let's keep going. So, okay, so please click on the butterfly graph. I'm going to look at, what was his name? Bishal. I'm going to look at Bishal's computer. And then you have the L matrix, so please click on that. And you'll get the L matrix, which has a semicolon at the end, so it doesn't actually display. Okay, if you remove the semicolon, it'll display. But it doesn't matter, it doesn't have to display. The next one is the eigenvalues. Everybody see that? Sorry, I sent you all the stuff with the outputs. If you want, you can remove them. But don't remove the inputs, okay? Okay, so you see the eigenvalues, and then if you click on the next one, you see the eigenvectors. And I have actually orthogonalized it. So you see the eigenvectors. Good? So in Mathematica, they always give it to you in the other order. Okay, the biggest eigenvalue comes first, then the next, then the next, then the next. So the eigenvectors also come in that order. Okay, so but we want to freeze from the smallest eigenvalues to the top, towards the top, right? So that's that. So then what I'm doing is, okay, so in line 25, you see the orthogonalized eigenvectors. You see the last one is 1 over root 5, 1 over root 5, 1 over root 5. That one is the smallest eigenvector. All right, so now we're going to do this construction, okay? So let's look at this construction again for the butterfly graph. So that the formula is over there. We're just going to do that construction. So the first thing you need to do is to construct the Y matrix. So we're going to freeze two of the eigenvalues and eigenvectors, the first two, and then we're going to allow the last three to be whatever. Is that okay? So we're freezing, so k is equal to 2, n is equal to 5, which is the number of vertices. Okay? So y has to be 3 by 3. Oh. It'll be okay? Okay, so let me calculate, let me go this far. So that was the graph. That's the named version. It's gone. Okay. All right, you can deal with it while we still continue, okay? So Y is a 3 by 3 matrix. Do you agree with that? Because I'm freezing the first two, I'm allowing n minus k is 3, okay? But it has to be PSD, so I'm inputting Y in a symmetric form, right? So if you actually type, if you do, at the end of Y, if you do matrix form, you can, so click on, do shift enter on Y, and then you will get a little panel that's, can you please do it? Shift enter on Y. Okay, so when you do that, you see a panel that comes up, and in the panel you can do display as. So click on display as, and you can see matrix form as one of the options. So click on that, and you should see that it's actually symmetric by construction. Okay? Everybody see that? Okay, so it's actually, is that okay, Anissa?
So which one is symmetric?
We are still up here. This Y matrix here. See this one. So if you do shift enter on that, and then you can display it. Okay, everybody got the symmetric matrix for Y? Okay, so then the next thing we need to do. Okay, sorry, I'm just going to turn it a bit. Okay. Okay, so the next thing I'm doing is I am reversing the eigenvectors. I'm going to construct the phi bigger than k. That's what I'm trying to construct, which I'm calling V, okay? So I'm asking to reverse the eigenvectors and then take the first three. So I really should have taken, no, what am I doing? Eigenvectors, 1, 2, 3. So what was the eigenvector? Okay, the eigenvectors were those, oh yeah. So I'm reversing the order of the eigenvectors, and then I'm taking 3 of them, but I'm trying to understand my own code. So reverse the eigenvectors.
So you are taking the first and doing the square of them in the reverse order.
Yeah. Oh yeah, that's right. So I'm taking the first 3 in the reverse order. That's actually what should be happening. Anyway, I'm picking the last 3 eigenvectors. That's what I'm trying to do, okay? And then I'm transposing that matrix, and you should see that in output. Can you click on these? Yeah, click on that, click on this. Yeah, so in output 34, we have this V, and then you see those 3 eigenvectors in matrix form in line 35. Do you see that? So this V is the phi bigger than K.
In the next line, you have to create those matrix forms which have the last n minus k, the p greater than
That's
k.
right, that's right. I'm just trying to pick out the last 3 eigenvectors, okay? So that's inside this matrix called V. Okay, so then what are we computing, right? So the next thing I'm computing is this thing. I'm computing this, okay? So the next thing we're computing is this V times Y times V transpose. You see that? Do you have a question? Somebody has a question?
We do not know what the matrix V is.
So matrix V is the last 3, is the top 3 eigenvalues, eigenvectors of the Laplacian. So if you go back and look at the Laplacian, you should see the last 3,
First 3.
in math, yeah, the top 3. So in Mathematica, it comes in the reverse order. So the top 3 eigenvalues are the first 3 eigenvalues, eigenvectors, and those we are putting into the columns of a matrix. That's the phi bigger than K, okay? So the notation is that what I'm calling V is phi bigger than K. And it should have 3 columns. Everybody okay with this? Yeah? And then in the next line, we are computing V times Y times the transpose of V. We're computing this. Okay? Do you have a question? Does anybody have a question? Please ask. Okay? So this piece, V, Y, this thing is exactly phi bigger than K, Y, phi bigger than K, transpose. Okay? So we finished computing what's in the circle here. This is the unknown part. So we just finished computing this in, I think, line 36 maybe. Yeah, line 36 we computed this. Now all this other stuff, right, this is fixed. So I'm now going to compute this part, and then I'm going to add the 2 together. Yeah? Okay, so let's continue computing. So what comes next, Vishal? Okay, so after line 35, we're in line 36. Okay, so the next command that says NF is equal to full simplify. Okay, what is it? In line 36, you see full simplify Vy V transpose. That just means that it just writes it in a nice way, okay? If you don't use the full simplify, you'll just get like a very messy expression. So all we're doing, so NF is not fixed. That's what it means, okay? NF means not fixed. That's the yellow bubble, green bubble. And that part is what you see in line 36. And you see it in matrix form in the next line. Line 37, you see the matrix form of it, okay? That's the green bubble. Now we're going to compute the red bubble. Okay, so for the red bubble, what all do we need to do? We look at I look at all the eigenvectors again, and I look at all the eigenvalues. Okay, I don't know what I'm doing here. Okay, let's just keep going. Oh, okay, so in this F part, okay, so what you're doing, you can do something clever, right? So you can just, so to compute the red piece, that red piece, we can just take all the eigenvalues, so both of these, and then you can take the eigenvector, the diagonal part to be the 2 that we are freezing, but after that we can just put the same ones again, right? You see in the red part, it is the first k eigenvalues are 0, lambda 2 up to lambda k, then it continues lambda k, lambda k, lambda k, lambda k. That's what I'm doing here. So this diagmat is just constructing this this diagonal matrix, okay? So in principle, this is, so what I'm doing is, this is lambda 1 through lambda k, and then after that you're just repeating lambda k, and then you're multiplying with the transpose of this matrix. Okay, that gets you the fixed part. Do you agree with it? So I'm just computing both those pieces at one shot by changing the diagonal matrix to be 0 through lambda k, and then lambda k, lambda k, lambda k, lambda k for the rest. Yeah? You can compute it separately if you want, and then add it. Okay, so F corresponds to the fixed part. That's the red bubble. Good? Now we have to add F to NF, right? That's to get the whole Laplacian, I have to add F to NF. So that's coming in line, 44. Yeah, line 44. We are adding everything together, and in the next line you see the matrix form of it. Everybody okay? Okay, please ask if you're stuck somewhere. So if you got to line, what is it, Bishop? 45. If you got to line 45, you should see the whole computation. The red bubble plus the green bubble, everything's added together. And you see that they are linear forms in the entries of the Y matrix. The Y matrix was filled with A, B, C, D, E, F. And they are all, every single entry is a linear function in A, B, C, D, E, F. Good? So that's our Laplacian. Good? But now you have to make sure that wherever there was no edge before, there is still no edge, right? We don't want extra edges. We only want to remove edges. So in the next step, this line 46, I'm saying that there are no edges in a bunch of places, right? So can you go back to the butterfly graph and check which edges were missing? So 1 is connected to everything, nothing is missing, but 2 is missing the edge 5 and 4, right? Yeah, so in this symbolic Laplacian we just constructed, you have to make sure that the 2, 5 and 2, 4 entries are 0, okay? You also have to make sure that the 3, 5 and the 3, 4 entries are 0. What's wrong, Kavya? Go back and look at the butterfly graph and see which edges are missing, not 3, 4 maybe.
3, 4 is missing.
Yeah, 3, 4 is missing and 3, 5 is missing, right? And similarly 2, 4 is missing and 2, 5 is missing. Is there anything else missing? Okay, so here is, let me just evaluate the whole thing.
Can you duplicate this place?
What's happening?
Mirror this place.
Oh. Okay, so do you see where all the equations come from? So in line, which line do we have it? Line 45. Yeah, in line 45 there should be 4 equations. Is that correct? So check that it's really the 2425, 3435. All those expressions must become 0. Yeah? Okay, so that's where the equations are coming from. And then we, sorry, where are we? 46, right? Okay, so what I did is I took those equations and I solved for them. That's the next command. Okay? So you can ask Mathematica to solve for it in variables A, B, C, D, E, F. And it's telling me that B is 0, C is 0, E is 0, and F is 4. Okay? So I get I'm forced to put those values because the equations already told me that there's some restriction on those. So then in the next one, we are just, what are we doing? So I'm doing full simplify. Okay, so I'm taking the Laplacian we constructed and we are substituting these values into the Laplacian. Okay, so the command, when you substitute, the command is /dot. So you take the object, you do /dot, and then you stick in what you want to substitute. So when you do that, you get this expression called new LMATs in line 48. Do you see? So it's simplified a lot, right? This big symbolic thing that we had before, when I stuck in the values of B, C, D, E, F, I got that.
Where are you making constraints? Wherever edges are there, it should be negative.
Not yet, not yet, not yet. I've only imposed the equations so far, okay? We haven't imposed that the edge positions have to be non-negative, less or equal to 0. Yeah, not yet. But from the equations already I simplified it a lot. Okay, so let's do that. That's what we're doing. So in line 48 you see the new matrix and you see also its matrix form. Do you agree? Now impose the condition that you have to be less or equal to 0 in all the edge positions. What do you get? What's an edge? Like, for example, one is connected to everything, but that's not helping us. Do you see one of the constraints we'll get? A is positive. Where does it come from, Abe?
Minus b by 2 is less equals to 0.
Yeah, if you look at the entry 2, 3, it says
Minus a by 2.
minus a divided by 2. That has to be less or equal to 0. That means a by 2 has to be greater equal to 0. That means a has to be greater equal to 0. Okay? So if you go in the edge positions and say that they all have to be less or equal to 0, you'll get constraints on the A. Is A the only thing left? No, D. A and D are left. So you'll get constraints on A and D, and that's it. So it's basically all matrices that look like the thing in line 49 with the condition that A is non-negative and D is non-negative. Okay? All right, homework. Yeah, this is it. Everybody okay?
Where are you?
We finished. We finished.
New LMATs is what you
Yeah, new LMATs. Okay, so let's check whether this made sense. So can you freeze the first 3 eigenvalues and eigenvectors and see what happens? What did we freeze right now? We froze the first 2, right? So we froze 0 and 1. That's what we froze. Okay. If you want, you can, yeah. Because we froze 2, we ended up with y being 3 by 3. Okay. If you freeze 3 of them, then y is only 2 by 2. That's even easier. So can you repeat the whole code? The nice version is sitting in the overleaf, so if you mess it up, you can download again. So let's just try the whole thing from the beginning. I just want you to freeze the first 3 instead of the first 2. Let's see what happens. We should get something really simple because we just have a 2 by 2 Y matrix then. See if you can modify the code to do that. Okay, so the first change has to come from Y. Y has to change. Until then, everything is okay. Yeah. AB and BC, because it's symmetric, right? So your Y should look like, let's do it. Okay, so Y should look like, you can call it whatever names you want, but like this. Okay? You okay, Nisa?
Yes.
Okay, excellent. So just click on it, and then in the V thing, you got to take not just 1 to 3, you have to take 1 to 4. No. Okay, this is the confusing part to me, this line. Yeah, exactly. Exactly. So you change the 3 to 2, right? Because we're allowing the last 2 things to be fluctuating. So you change this number 3 to 2. Okay? So this is the transposed version. That's why it looks kind of weird like that. But in the next line, you should be able to see a matrix that has only 2. So this V is the phi bigger than K, okay? So V is phi bigger than K. This should now have only 2 things in it. Yeah? Didn't work out?
See, eigenvector Q1 and the output is this. Output is this. Because I
Can you run, this is not, this is some simple error, so let's see.
There are 5 vectors in output.
Yeah, so just evaluate from the beginning, from the top. Yeah, just click Shift Enter on every one of them, on each line. No, not there, like at the end of this line.
Input line, not the
Yeah.
output line.
So do Shift Enter, and then do that. Did anybody, other people okay? You got 2 vectors? No? Okay, it's complaining for everyone. Okay, you may have to reevaluate from the top.
If something is not run, it will be blue. If not run, G. Then the thing is done.
Okay, so V is okay, A, B, B, C. Matrix form is okay. Let's try this now. Okay, okay, if you have to reevaluate from the top, okay? It's not going to just start in the middle.
It says input 18, right? Here it doesn't say anything.
Question?
So it's not evaluated.
So you should get V to have 2 columns, and it should be the last 2 eigenvectors. Let's take a look. Can I go through here? Oops. All right, what's up? So change, it's because you have to reevaluate from the top. So go here and do Shift Enter on every one of these, okay? You can evaluate the whole notebook, but the later things you still have to change, right? So you shouldn't evaluate the whole
Can I
notebook.
delete the output, then re-evaluate?
You don't have to delete, it'll just come again. Don't worry about deleting, but just run all the commands. Yeah, run this, yeah.
Keep going up. See, G is also blue, so it doesn't know what G is. See, there is no pin one.
It works now?
Yeah.
Okay, great. You can keep going. Okay, so up to here is just the data. Now this is where we are changing things. So Y is fine, and your Y is fine. Now let's try this. Okay, works, right? So then do the matrix form of it. And
Color will change. So G
yeah,
is blue,
good?
became black.
Okay, everybody okay?
L is not blue, it doesn't know what.
You got 2 vectors too? Okay. All right, so then what happens? Did you keep going after that?
We are getting only one
What?
2, 4, 2, 5 same equation.
Yeah, it's fine. That's okay.
But it is showing equation number.
It's just saying B is 0, C is 4.
Okay.
Right?
So this
That's
error-
okay. It doesn't matter. It just doesn't, yeah, leave it. It's not error. It actually gave you something. Then you're happy. Okay? So keep going. Yeah, Anissa, let me help you.
Why this V for me, there are 5 vectors in R2.
Yeah, this is the transpose. Okay? This is the, see, I put a transpose here. So this, now click on this. Shift enter. Yeah, now you see these are the 2 that we are not freezing. Okay? And now click on this.
Yeah, but before that, it's not showing me the.
It doesn't because there's a semicolon there. If you remove the semicolon, it'll show, but it's kind of a messy thing. It'll give you just some weird thing so that we suppress it. Okay, if you can click it though, if you want.
No, but it's.
It's okay, just go here and click on it. Yeah, see, it gives you just that. That's why I always suppress it. And you can display it as a matrix if you want, but I don't bother with it. Okay, so you're good till here. Now click on this. Okay, and then go down and then you can look at it in matrix form.
So this is the non-fixed part.
Yeah, and then click on this.
Matrix.
Yeah. I mean, okay, hopefully that's correct. You did shift enter, right? Okay, so this should be how it looks. Okay? And now this is we're computing the fixed part. So you got that. That's all the eigenvectors again. This is all of them again. Yeah. Then go up. And now here we want to freeze 0, 1, 3 and then 3, 3.
So this is something I did not understand. How are we choosing these values?
So I'm computing the red bubble.
Yes.
So the first k eigenvalues are 0, 0, lambda 2, lambda k.
Right.
And in the next piece, you see what we're saying is that if I took the lambda k inside as a lambda k identity, we're making a diagonal. All of those entries are lambda k,
Right.
the last one, okay? So we are, where are we now?
But
Here,
the yellow
yeah.
one.
So we're freezing 0, 1 and 3, and then we're saying the next 2 are also 3, 3, 3, 3, 3, 3, right? That's what's happening there. So I'm making a new diagonal matrix like that. And now, click on that, then you should see that diagonal matrix.
This is the diagonal.
Yeah, and then you can see it in matrix form. Yeah?
Diagram will also change.
Yeah, because diagmat should be 0, 1, 3, 3, 3. Because we want to freeze 0, 1 and 3. And then in that red piece, we are saying that the rest are all 3, 3, 3, 3, 3, right?
0, 1, 3, 3.
Yes, so this is a diagonal matrix.
Yeah.
And I'm changing the basis.
Yeah, that's right. And then do matrix form of that. Yeah, and then add the 2 together, the fixed part and the non-fixed part. So now this is how it looks, right? You can also do it in matrix form. Okay. So good, you got all that. And now we want to again take the constraints that have to be 0, which are the same because it's the same graph. So you get this. And now you want to solve that set of equations, which are called CNSTS. And then you'll say that B has to be 0, C has to be 2. Okay, so now let's substitute it into the matrix. Okay, that's our matrix. Let's look at it in matrix
So
form.
it substitute it in the same orders.
Yeah, it just set B equal to 0, C equal to 2 in this. Okay, so then now look here. Yeah, so this is now how the Laplacians look. Okay, now you have to impose the condition that wherever there was an edge, it's less or equal to 0 and see what comes out. That way, just do by hand. So the edge, the non-edges, the edges you have to do, right? So the edge, all the edges will give you some conditions. Okay, who is stuck? You are, Lavanya stuck? You're stuck? Okay. Let's see if how I get to you. Can I just go through here? Okay.
Up to NF, it's okay.
Yeah.
From U, why we are choosing all those factors?
Because I'm trying to compute the red piece, okay? So the red piece has all the phi k's, and then on the other side it has the phi greater than k's. So I'm choosing all of them, and then I'm declaring the new diagonal matrix to be lambda k, and then after that it's little lambda k times the identity. So it's like you can pull that little lambda k into the middle of the phi bigger than k, phi bigger than k. So the new diagonal will be 0, lambda 2 up to lambda k, then lambda k, lambda k, lambda k, lambda k, right? That's what's happening here. So that's why I'm choosing all the eigenvectors. But here we are freezing 0, 1 and 3 and then 3, 3. Okay? So 0, 1 and 3 first. And then comma 3, comma 3. Do you understand what's happening? Okay, so that's your new diag. Now that you're done. Now just keep evaluating. And then this will now be the fixed part, right? So it's just a trick to do it at one shot. And now you can see the matrix form of that. Yeah, good. And now we're going to add the two together. Good. And then look at the matrix form of that. Yeah. Then we're going to set all the edge things to 0. It's the same non-edges. So try it.
It will be same.
Same, right? The butterfly graph has the same, right? So you get something and you're asked to solve it. Just the equations. You get that. Okay? Now you're going to substitute this solution into this matrix. That's what this is doing. L maths, substitute. You got that. Look at it.
Madam, what is this error?
That's just because it thinks it's not giving you answers for A and D and all that, right? Yeah, it's just saying.
For like LST should be less than equal to
Yeah, so impose that and see what set you get.
that condition.
The less or equal to 0. I mean, it's not written here. You can just write it in a piece of paper.
That graph also. That I
Yeah, so just see where the edges are, right? The edges, like 1 is connected to everything, 2 is connected to. So the only interesting things are probably, yeah, so you remember the edges, right? So 4, 5 is an edge, 2, 3 is an edge. So let's go look at those. So 4, 5 is an edge. Do you get anything interesting?
5, then it should be less than equal to 0.
Correct. And 2, 3. It's already fine. So just that, maybe all, yeah. So these two are the only interesting things. They're symmetric, right?
For that, like 1 plus a by 2 should be greater than equal to 0.
Yeah.
And it should like a by 2 should be greater than equal to minus 1, and that a is greater than equal to minus 2.
Yeah. Right? That's the only condition. No other variable is here. The B and C got fixed, right?
Yes.
Okay, so let's write the answer. Sorry, Devendra, I'm going to go through here again. Okay, what's the answer? Oh, yeah, that's not a serious problem, right? Okay, does anybody have the answer? So how many parameters do we have? I mean, so there is some big L, right? You got some big L. But that's what's, only one variable should be left. Do you agree? A. And what's the condition on A? A greater than? Like this?
Yes.
Okay. So then the parameter space, do you see the parameter space? It's one dimensional, right? and this is 0, this is 1, this is minus 1, minus 2. So it should be everything starting from here going forwards, okay? So can you what's the butterfly graph that corresponds to this dot, right when A is equal to minus 2? Which edge will disappear?
Which edges, which entry of L max becomes
A was so 4 5.
4, 5?
Right
4,
side is
5,
4,
yeah. So in this extreme edge, we should have that 4, 5 disappears. 4, 5 is these two, right? Okay.
No.
2, 3 also disappears?
2, 3 is already gone.
2, 3 is already gone? Okay, so you really only have this, just at this end. Then here what happens everywhere else? 2, 3 is already gone. And this, oh, sorry. This is 2, 3? 1, 4, 5. So 4, 5 is there, and it has, what's the value on it? So whatever you see in the L, you have to negate it, right? That's the weight. What do you see in the L? Okay, 1 plus A over 2. So 2, 3 is really gone from the beginning? What? Because in the 2, 3 position, do you see a 0?
No, 2, 3 is there.
2, 3 is there? Okay. All right, let's do it again. Let's do it again. This is 1, this is 2, 3, this is 4. Okay, I cannot see the answer, so I'm relying on you to tell me.
2 3 is minus 1.
Okay, 2, 3 is there and it has weight 1, right? Okay, so 2, 3 has weight 1, it's there. Okay, all these inside things still have weight 1? Yeah, so this is weight 1, this is weight 1, this is weight 1, this is weight 1. But this edge is gone, right, for the very first dot? And then these are all 1 again, right? And this is this. That's kind of weird. Oh, yeah, it makes sense.
Why are we evaluating minus 1 minus A by 2 as 0? Why are we substituting?
No, we're saying that when you're at minus 2,
okay.
when A is minus 2,
But how did we get that A equal to A greater than or equal to minus 1?
from this condition, right? So the only condition is that this guy, this is an edge position,
Right.
this has to be less or equal to 0. That's the weight of that edge. So minus 1 minus A over 2 has to be less or equal to 0. That means 1 plus A over 2 is greater equal to 0. So 1 is greater equal to, or A over 2 is greater equal to minus 1, A is greater equal to minus 2. Okay? So the full range is from minus 2 to infinity, the value of A. But at minus 2 itself, it'll completely lose the edge 4, 5.
But I'm sorry about this question, but why this should be less than or equal to 0?
Because it's a Laplacian, right? Because it's a Laplacian, the way in the edge positions, we put the negative of the weight. Got it? The diagonals are unimportant because they're just getting added up. That's not important. So the only interesting edge is this edge.
Yes.
That's the only thing that has a function on it. That has to be less or equal to 0. So that tells you the range of the A's, right? And in the extreme end, you will lose that edge. But everywhere else, you will have that edge, but it'll have a weight depending on A. It's 1 plus A over 2.
And accordingly, the diagonal entries will change.
Yeah, exactly. Yeah, diagonal entries are just tagged, so we don't need to worry about it. Okay, who else? Question, Abe?
There's something, okay, we started with the symmetric matrix.
Yeah.
The other conditions were positive, semi-definite things, are they not considered like that?
In this case, oh yeah, we didn't actually check that it's positive semi-definite. Yeah, we can prove that this construction will always give us something positive semi-definite, right? Well, what's the easy reason, right? By construction, you have made sure that all the eigenvalues are non-negative. By construction, right?
Talking about L.
L.
I'm talking about L. In the code, we put Y. We started with just a symmetric matrix.
Oh, okay. Y is PSD. Oh, yeah. Maybe we need to impose that too. Okay, let's think about that. It's a good point. Okay, Abhay is saying we need to worry that Y is PSD. Yeah, good. Okay, what is Y at the moment? We've already solved for some parts of Y, right? So B is 0, C is 2, and this is A. Okay, yeah, actually very good point. So A is A, so we need this to be PSD. So the only thing we need is A greater equal to 0. Actually, we do need this. Yeah, okay, very good. So we made a mistake.
So we have to take the intersection of those.
Yeah. Good point. Thank you. Okay, so now let's look at it. So A has to be greater equal to 0. So this is the A line. I think that's true. Yeah, so exactly. So then the set seems to only go from here onwards, right? Okay, so the set only goes from here onwards. That means you don't actually lose any edge. Right, so these are weight, all of them are weight 1 except the edge 4, 5. This is 4, 5. And on 4, 5 we have the weight
Minus 1 minus A by 2.
1 plus A by 2, right? Yeah, so this one will have the weight 1 plus A over 2. Yeah, so it looks like we can't actually remove any edge.
No, but we have, this is we have cut the 3 dimension, the eigenspace corresponding to lambda equal to 3, that is 2 dimensional. We have taken 1.
We have taken 1. Okay, maybe try it the other way. So still freeze 3 eigenvalues, the first 3, but instead of freezing you froze one of the eigenvectors of the eigenspace with eigenvalue 3, right? Freeze the other one. Let's see what happens.
So this mathematical syntax is a bit tricky because they have to take the first and the third. So
Yeah, so let's actually write the syntax for it. Let's write the syntax. It's working? Okay, so let's try that. Let's try if we get a different thing. Okay, do you see what I'm trying to say? Because eigenvalue 3 had multiplicity 2, right? So we chose to freeze the first 3 eigenvectors in the order Mathematica gave us, but we could freeze eigenvector 1, eigenvector 2, and eigenvector 4. That also corresponds to eigenvalue 3. So let's try that. See if we get a different answer. Okay, so you have to start again from the beginning, okay? Otherwise it's not going to work. So here's the butterfly graph. Is it coming? Yeah. So L is there, eigenvalues are there, eigenvectors are there, and Y has to become small. Yeah, A, B, B, C. And then here, we're going to take,
instead of 1 to 2, you should take I in the
Yeah.
set 1, 3. So just put braces around 1 and 3.
okay, so just, oh, like that. 1,
And end it at 3.
oh, but
After 3.
I want, is this what I want?
Yeah. Not run it. You'll just get two vectors, which is the first and the third.
I see. So we are not freezing the first eigenvector in Mathematica order, and we are not freezing the third eigenvector in Mathematica order.
So when you
Let's see what comes out.
switch it off.
Yeah. So please check that these two are the the largest eigenvector and the eigenvector of 3 that we did not freeze before. So we can look at, what was that eigenvector stuff
We are
though?
taking these two, 5 and 3.
Yeah,
So this one and this one, these two go.
yeah,
You're not taking these two, you're taking these two. First and third. And the syntax for that is to put braces around 1, 3. So when you take I in a set or a list, it will take only those elements. If you do I, comma 1, comma 3, it will go 1, 2, 3. I, comma 1, comma 5,
Yeah.
it will go 1, 2, 3, 4, 5. But if you do I and then a set, it will just take those things in that set.
yeah. So do you see that's exactly what we are freezing, right? We are freezing the first eigenvector, which is the top eigenvector actually, and we're skipping the next one and then freezing the third one, right? So it's a different one that we are freezing. Okay, great. So everybody okay? All right, so we froze, we got that, and then we can still, this command is still the same. So we are calculating NF, and we got this. Okay, so NF should look like this.
But the third thing is the other eigenvector, not the. So in the no, two frozen. The non-frozen part is.
Everything else is the same as before.
Yeah. So
A is what? 2. You get that?
Here, can we take
Yeah.
1, 3, then 4, 5 also?
No, because then you will get lesser stuff, right? Because if you're forcing the eigenvalues to be something else, all we can say is that the eigenvalues of the unknown part is at least 3.
Ma'am, actually, because
that's already reversed.
it can be equal to lambda k,
Yeah,
or it can be greater. So,
it can be greater, but
what
if
happen
you,
if we take greater values?
you'll just get a smaller collection of sparsifiers. You're sort of putting an extra thing on it, right? You're saying that it's not as free as possible. If you put 3, 3, 3, 3, 3, then I know that it's, yeah. Then you know that I'm allowed to take anything as long as it's bigger than 3. If you put 4, 5, then it's saying it has to be, the next one has to be bigger than 4, the next one has to be bigger than 5. That's extra, right? So you'll get a smaller set.
Oh, actually, she's right.
What?
So we have to be careful about you.
Oh yeah, you have to be careful about you. Okay.
So you, we have to reverse these two, right? So
Yeah, it's kind of a mess.
Can we give orders for the eigenvectors?
No, we'll do it in a second. Okay. So I have to put what?
So here you have reversed the eigenvectors.
Yeah. So we have to be careful about u. Okay. So let's build u carefully. So u is going to be
Transpose of eigenvectors for
okay, I'm just going to do it the very simple way. So it's going to be eigenvex 5, that's the last eigenvector. Eigenvex 4, and then eigenvex okay, so yeah, that's right. So 1 and then this is still 3, right? Okay, I need somebody's help now.
2. That should be 2, then 3.
Now we're writing the eigenvectors in the reverse order. So 5, then 4.
Then 2, 3, 1.
2, 3, 1.
2, 3, 1. 2, 3. Okay, I think this will work. Okay.
Transpose of this one.
Okay, is that the right order? Can someone check? So we should be freezing eigenvector 1, 2, 4, and allowing the other two to be free. Okay, did people understand this comment, why we had to do this? No? Okay, so we messed the order, right? We changed the order, so you have to be a little bit careful. Let me write it here, maybe it'll be easier. So in the beginning, we had this U matrix that consisted of, Mathematica gave us, what Mathematica output is phi5, phi4, phi3, phi2, phi1. This is how Mathematica gives you the eigenvectors, from biggest to smallest, okay? So the ones that we are freezing are this one and this one. And then instead of freezing this, we froze this in the second time, right? The eigenvalues are, these two go with 3, this is 5, and this is 1, and this is 0. These are the eigenvalues, okay? So the ones we are freezing is those 3. So all we're doing now is we are writing the U matrix so that phi1 is first, then phi2, then phi4, those are the ones that we are freezing, and then phi3, and then phi5. That's what we're doing, okay? So we just changed the order so that the first 3 are frozen and the other 3 are not, okay? And then the eigenvectors, the diagmat should still be eigenvalue 0, eigenvalue 1, eigenvalue 3, 3, 3. This is still diagmat. Okay? Okay, so just make that small change and then we should be good. Seems we're getting the same thing, right? Are we getting the same thing?
Yeah, it's just the position of...
Yeah, but now some other edge is being affected.
No, 2, 3 and 4, 5.
Exactly. So before it was the 4, 5 edge that had weights on it. Now it seems to be the 2, 3 edge that has weights on it. So it's pretty symmetric. And it's also the same, right? The range is the same. So A is at least -2 according to this, but then from the PSD it's at least 0. Everybody got this? Anybody stuck? Happy to help?
So 5, 4, what were the indices for
2, 3, 1. 5, 4, 2, 3.
Oh, this bit? This here. All right, right? What happens if you freeze the first 4 eigenvectors? Can you repeat very quickly? It's going to be really easy because the matrix Y has just one entry, A in it, right? And there's no messing with the order or anything, so you can go back to the old.
Just we will freeze 1. We will freeze just 1.
Yeah, so in the V matrix you go I, comma, 1, 4, 1, comma 4. You don't need the braces anymore, right? What Arvind showed you. So you just go 1, I, comma, 1, comma 4. So that freezes the first 4 eigenvectors. Here, let's do it. So I want to change, the Y matrix just has one thing in it.
Yeah, it should be double brace because it's a matrix.
It's a matrix, so it should be double brace.
It's a 1 by 1.
But then here you just go 1 to 4, like that, and take out the braces. Like that, right? Okay, so you should get the top 4 eigenvectors inside your V matrix.
5 by 4.
Yeah? Everybody good? So we just went back to the old code where you just have I, comma 1, comma 4. That means your you're freezing 1, 2, 3, 4. Oh, this is the part we don't freeze, right? I'm so confused now. V is the part we don't freeze. Yes, so what should we write there? Yeah, it's just one single eigenvector. Yeah, one single eigenvector. So what? So it's just the.
V equals 1 to 1.
Yeah, y is a singleton, yes. So let's just write this as
I 1 to 1.
I1. Yeah, okay, 1 to 1. That'll work.
One more bracket is missing.
Okay. Okay, it should look like that. That's V. This is the thing we're not freezing. Okay? That's the V. Okay, then everything else should work. So this is the this is the NF. That's NF. And now in the U matrix, we can take it in the usual order.
Or this.
Or
Doesn't matter.
Doesn't matter which order.
Only the fifth is. So we have interchanged 2 and 3.
Okay, yeah, it doesn't matter. So we can take this in the U matrix. And then in diag, it's now 1, 3, 3,
And
5. Is that right?
because it's you want the last.
No, I think we still want 3. Because we are freezing the first 4 eigenvectors, eigenvalues, 0, 1, 3, 3, and 5, right? So we're freezing these, and we want this one to be at least 3. So it's still 0, 1, 3, 3, 3. Okay? Okay, good. Okay, we got that. We got diagmat, and we got this. And we got F, and we add the 2, and we look at it. Should look like this. Does it look like this? No? Okay, so there's only one constraint probably. Okay, that's what that is. And then, yeah, so it goes A is 2. Okay, and A was the only thing in the matrix. Yeah,
That will come back to the Laplace.
that's right. So it'll come back to, that's what you're saying, Vishal? Yeah, you just get back the original Laplacian. Okay, so this tells you that what does our conclusion? If you freeze the first 4 eigenvalues and eigenvectors, the only sparsifier is G itself. Okay, G is always there in every sparsifying set, right? Because G definitely has the properties we're looking for. So the only thing in it is the set G itself. Okay? There's no sparsification. Yeah? So the complete graph is an example of one where you can sparsify at every level to the end. So in a complete graph, this won't happen. Even at the very last step, it'll sparsify. Of course, if you freeze everything, it's fine. It won't move. But even up to the second last eigenvector and eigenvalue, you can freeze and it'll sparsify. It'll actually lose edges. So there are some graphs for which this will happen. Some graphs like this one will stop sparsifying. Can you tell me a natural bound where it'll stop sparsifying based on that stuff? So what's the dimension of our parameter space from that model? So the unknown vector is y, right? Y is basically the variable inside the model, right? How many variables are there inside y? It's an n minus k symmetric matrix. How many unknowns are sticking in, do we have to stick in it?
For a 3 by 3, how many are there?
So the number of yij's is n minus k choose 2, right? It's a symmetric, what?
Diagonal. Freedom and plus.
Oh.
Yeah, for 3 by 3 it's 6.
Okay, so it's maybe n minus k plus 1 choose 2. Okay, something like this. Okay.
3 by 3 you have 6.
Yeah. Okay. Yeah. Okay. Yeah, okay. It's n minus k times n minus k plus 1. That's true. Okay, this is the number of variables we have, right? And then we also have all those equations, right? We have the equations that LST is equal to 0 every time ST is not an edge. So these are equations that we're imposing in this dimensional space. So we're living in space that is, so everything is happening in this space, right? The parameter space is isomorphic to R to that number, and we're imposing a lot of equations. So if you impose too many equations, what happens generically? Every equation is cutting the dimension of space down by 1, right? If they're independent. Maybe they're not independent, but let's assume generically what happens. So how many equations can I impose and suddenly have no solution? I mean, G is always a solution, so other than G. How many equations do I need to cut that space down to a point? Okay, I'm going to give this number a name, okay? Let's call this number T. How many equations should we impose in T-dimensional space to cut down to a point? T, right? In two-dimensional space, you need 2 lines to cut down to a point. In 3-dimensional space, you need 3 planes to cut down to a point, like the orthons, right? Orthon walls. So in T-dimensional space, you need T equations generically to cut down to a point. Now, if the equations are dependent and all, you need more, okay? So generically, assuming there's no dependency on the equations, if you impose T equations, you'll just get the point as the answer, and that has to be G, right? Because G sits in this sparsifier set. So we can never get rid of G, right? So how many edges can we be missing from the graph and still expect something non-trivial as a sparsifier? So can we write a statement? If we are missing so many edges, you shouldn't expect to see a sparsifier other than G. So we're living in RT, and these are all equations coming from missing edges, right? So if G is missing, if G is missing T or more edges, right? T or more edges, then we expect that the sparsification set, SPKG, is just G, nothing else. This is what we expect, okay? But this is an expectation because it depends on if your equations were dependent or not dependent, and there are counterexamples in both directions. You have graphs with lots of missing edges, too many missing edges, that'll still sparsify, and there are graphs with not so many missing edges that won't sparsify. But if you run this algorithm on a random graph, you'll get exactly this threshold. Okay? So generate a random graph in Mathematica. There's a command, and then run this whole thing that we just did, and you'll see that if it's missing exactly T edges, where T is the dimension of the number of variables in the symmetric matrix, then you will stop sparsifying. Okay, so that's what the last 2 exercises are about. So if the very last exercise is asking you to calculate. So it's saying we call this a linear algebra bound. So I'm asking you, use the linear algebra bound to determine the largest k for which a graph with 10 vertices and 30 edges will not sparsify. So n is 10, the cardinality of E is 30. So what's the largest k we can get to before we think it will stop sparsifying? Maybe, you have to do that calculation, right? So if we have, so you should be missing, so k we don't know, I'm asking you to find k. So n is 10, okay. K we don't know, we'd like to find k. So if you're missing t or more edges, you'll stop sparsifying, right? So that means, how do we do this calculation?
So n choose 2.
So n is 10. So 10 minus k plus 1, choose 2. This is t, okay? This is the maximum number of edges you're allowed to miss, right? This is 15. K we don't know.
No, on 10 vertices and 30 edges.
Yeah, 30 edges. Okay, so we want this number to be less or equal to 30, which is the number of edges, right? These are the missing edges, sorry.
Less than 15.
Okay.
Choose 2, right? Less than equal to.
So how many edges are missing if you have,
So 55 is, no, 45 is the maximum number of edges.
yes,
We
exactly,
have 30 edges. So
exactly,
15 are missing.
exactly. So you want this number to be less or equal to 15? These are the missing edges? Okay, and then you have to calculate what k comes out of this. Okay. So there is this natural nice bound that tells you that, so in particular some graphs will not sparsify if you pick certain k. So it's a very different type of result from Spielman-Teng. Okay. K is 4? Okay. So it's the biggest k you can make so that this happens, right? Yeah. So you just solve the inequality and see what's the biggest I can push k so that this binomial coefficient is less or equal to 15. It's okay? All right, I think that's a good place to stop. If anybody was stuck on the code, I'm happy to help before we, yeah.